The final topic in this chapter is the subject of general linear systems. And this is a pretty big topic. We'll probably spend about a day and a half on it, section 1.8. So far, we've really been focused on a particular kind of linear system. We've said that A is an n by n matrix. And we've really been focusing on the non-singular case. And in effect, everything we've done has been basically to say, if you have an equation like this, A times X is equal to B, one way or another, the way you solve this is by taking the inverse. You write X is equal to A inverse B. And the non-singular case, of course, is to say that the inverse exists. And one of the things we've done is talked a little bit about techniques for finding the inverse. In particular, if you write A is equal to LU or PLU, then you can find its inverse as A inverse is equal to U inverse L inverse. And if there's a P, then also the P inverse. And one obvious fact, which I haven't really emphasized, but stands out from this, is that there is a solution and it's unique. So the fact that there's a solution, I've written it down. You compute A inverse and that's it. And that's the only solution. That's the only way to solve this equation. And now when we talk about general linear systems, we're going to not be in that situation. In a general linear system, we're going to change two things. First of all, we're going to say that A is no longer necessarily a square matrix. It's going to be a possibly m by n matrix. And even if it is square, it's not necessarily invertible. So let's do an example of the second one first. That's a square matrix which isn't necessarily invertible. I'll just do a supremely simple example. Suppose you had a matrix like this. And you had an equation x, y, z. And let's say we wanted to solve this is equal to 4, 4, 0. Well, we haven't, strictly speaking, really discussed this kind of example because this is not an invertible matrix, this 0 here. All right, well, let's see what happens. This is very easy. So if you proceed by back substitution, you look down here and the last equation gives you 0z is equal to 0. Now, what does that mean? 0z is equal to 0. I could take z is equal to 0. But I can take z as equal to anything. This is no condition. So z is anything. And this holds. So that's a new feature. And after you do that, the next two equations are very familiar. The next one, when you go back a step, you get y is equal to 4. And then from the first row, you get 2x is equal to 4, which is to say x is equal to 2. So the general solution to this equation is x is equal to 2, y is equal to 4, and any z. So let's redo this example with the same left-hand side, same matrix on the left, and the only thing I've done is I've changed this last coordinate in the target vector. And when we do that, the very first step of the back substitution, we have to try and solve 0 times z is equal to 1. And that's a shame because that has no solutions. And therefore, this equation has no solution. So this is a new feature of this type of equation. If A is singular, there's two kinds of things that can happen. It can have infinitely many solutions, or it can have no solutions. So that's in contrast to the non-singular case where there was always exactly one. Let's look at a different kind of example now. Here is a system of 3 equations with 4 unknowns. Since the number of equations and the number of unknowns is different, this is no longer a square matrix once you convert it to a matrix equation. So let's see how that works. So there are 4 variables, x, y, z, and w. So let's start with that. X, y, z, and w. And I'm looking for some matrix equation. Well, I want to multiply a matrix by this, so it better be a matrix of size 4. And the first row is these coefficients, 1, 2, 2, 3. So when you multiply this times this, you get this equation, this left-hand side. And there are 3 equations, so this is going to be a 3 by 4 matrix. And the second row is 0 times x, 2, 1, 1. And then the last row is 0x, 0y, 3z, and 1w. And the equation becomes this is equal to 3, 4, 2. Okay? And this is a I've picked a very simple example where this equation, really no further work is necessary in order to solve it. The fact that it looks like this means it's the analog of upper triangular like before. There's an extra column, but aside from that, this is basically the kind of thing we've seen before. And you can solve this by back substitution. So I'll just write out the first equation would be 3z plus w is equal to 2. Now, what's new here is that back substitution doesn't give you a unique solution, but given w, it tells you a unique z. And so what you can do is you can bring w to the other side and write 3z is equal to 2 minus w, or z is equal to 1/3 2 minus w. Okay, and what w is going to be what we call a free variable. We're going to be free to choose this however we want, and then the other variables are going to be expressed in terms of z. So, for example, when you go back one step, you get the equation 2y plus z plus w is equal to 4. And that expresses y in terms of z and w, 4 minus z minus w. And, well, the z is in terms of w, so that's 4 minus 1/3 2 minus w minus w. And you could divide both sides by 2, and that gives you y. And I'm not going to work out what that comes to, but you see, again, y is expressed in terms of w. And then when you go back one step, you're also going to get x is expressed in terms of w. And that's what we mean by the free variable. There's one free variable, and then all of the others are determined. Okay, so that serves as an introduction to an important concept in this chapter, which is called row echelon form. And we say, so row echelon form this is a generalization of the form that we've been using for solving non-singular n by n equations. And the idea is that you start with some, I'll just do an illustrate with an example. You start with some matrix which has, say, a 1, 2, 2, 0, 3, 4, 5. And the next one starts off with a 0. And maybe then it has some non-zero number like 1, and then it can have anything. And the next one necessarily starts with a 0 and another 0, and now it's allowed to have extra zeros. So an example would be this. And then every time you have a 0, these things are called the pivots, just as in the non-singular case. The first non-zero entry in a row is called the pivot, and just like before, everything below the pivot has to be zeros, and everything here also has to be zeros, everything here. And now we're allowed to have a non-zero entry here, so for example, it could be 4 and then 1. And so these numbers here are called the pivots. 1, 1, 3, and 4 are the pivots. And this matrix is in row echelon form. So what row echelon form is that let me draw a line here. There's sort of a staircase like this. Everything below the staircase is 0, and the first non-entry in each row is non-zero, and those entries are called the pivots. Now, in this example, all of the rows had a pivot, but that's not a necessary condition, so let me draw a more general kind of example. A more general example would be something like this. Whoops. Got a little bit of drift there. And then the last row, all zeros. And what this matrix indicates is that what's up here can be anything. So this stuff here is allowed to be anything. And in this example, the pivots are 1, 2, and 3. And here's the staircase. Everything below the staircase is 0. In particular, there's a certain number of non-zero rows towards the top of the matrix, and then a certain number of rows at the bottom. excuse me, a certain number of 0 rows at the bottom. Okay, so here's our matrix again, and now let's suppose that this was actually part of the matrix of a system of linear equations. So this matrix has 8 columns, and so we have 8 variables, x1, x2, down to x8. And when you multiply these two, since this has 5 rows, we're getting something with 5 entries, and let's make them 2, 1, 1, and the last two 0. And when you go to solve this, if you actually try and solve the corresponding equations, it's quite easy. The first thing that you notice is that these rows, excuse me, these columns where there's no pivot, basically don't do anything, and the corresponding variables are x3, x4, not x5, but x6, x7, and x8, and it turns out that those are the free variables. You can set those to whatever you want. And then the remaining variables, x1, x2, and x5, are in terms of those. So, for example, when you look at this last row here, you get 0 times 0 is equal to 0. That's why I put a 0 there. And similarly, the second one is 0 times 0 is equal to 0. And then when you look at this row right here, whoops, you get something of the form 3x5 plus something involving x6, x7, and x8 is equal to 1. And by this I just mean some combination, some sum of these terms with some coefficients coming from here. And you can solve this for x5 in terms of the free variables x6, x7, and x8. And then similarly, when you look at this line here, you get 2x2 plus all of the remaining variables, something involving x3 through x8, and you set that equal to 1. And x6, x7, and 8 are free. x5 you've taken care of, and x3 and x4 are free, and you wind up with x2 is equal to something in terms of the variables x3, x4, x6, 7, and 8, and so on. So that's just an overview of the way these, the reason that row echelon form makes an equation very easy to solve. Okay, that brings us to an important definition in a couple of important definitions in the theory. So the setting is we have a matrix A in row echelon form. Then the rank of A is the number of non-zero rows. Which is just the same thing as the number of pivots. And the basic variables are those correspond to the columns with a pivot. And the free variables those are the ones which correspond to the columns with no pivot. And if you think about it for a minute, it's clear from what we just said that the rank, what's the rank again? The rank is the number of pivots, and there's one basic variable for for each column with a pivot. So the rank is just another word for the number of basic variables. And the idea is that this information controls the nature of the solutions of any corresponding equation. If you have an equation with free variables, if it has any solutions at all, it has a family of solutions where you're allowed to vary those free variables, and the basic variables are expressed in terms of those. Okay, so let's go back and see where we are. Suppose we have an m by n matrix and a fairly random equation, x1 down to xn, and there are n variables, and since it's an m by n matrix, the target vector has m coordinates. We have a general equation like this, and I haven't really discussed this yet, but I mentioned it. We're going to do row and column operations to reduce A to a matrix in row echelon form. So I haven't talked about this process yet, but it's just a generalization of Gaussian elimination. So I'm just discussing what happens when you get there. So let's assume that we've done that already, and this A is in row echelon form. And I want to say what we can, a general theorem about the structure of the solutions of such an equation. So I'll state it as a theorem. The possibilities are the following. The equation has either no solutions, exactly one solution, or infinitely many solutions. And let's say a little bit more about when these things happen. Let's consider a fairly general situation. So suppose you have an m by n matrix, and we have an equation of the form a x1 xn is equal to some vector b1 bm. And I haven't really talked about this yet, but there's generalized Gaussian elimination allows you to reduce A by row operations to assume that it's in row echelon form. I haven't discussed that process yet, but let's assume that we've done that. And the question is, what can we tell about the solutions by the properties of this row echelon matrix? And I'll state this as a theorem. There are a couple of possibilities, and I'll say it this way. Either the equation has A, no solutions, or B, a family of solutions given by the free variables. So what this last means is that either there's no solution, or if there is one solution, at least one solution, then there are a whole bunch of solutions obtained by arbitrarily varying the free variables. And so in this second case, you can break this down into two subcases. B1, there's a unique solution. That's what happens when the number of free variables is 0. There are no free variables. And the second case is there are infinitely many solutions. If there's at least one free variable. So there's sort of two questions. Are there any solutions at all? And then if there are any solutions, the number of them is controlled by the number of free variables, which is to say the rank of the matrix. Well, it's related to the rank of the matrix, and there's either exactly one solution or infinitely many. We've already seen examples of each of these. Let me just do one or two more examples to illustrate what this is about. So, for example, suppose I had a row echelon matrix that looked like this. And then anything up here and anything up here. And so this has some large number of variables. And the equation is saying set this equal to something, well, I guess I'll call it A, B, C. How many solutions does this have? Well, the first thing is, does it have any at all? And the question of whether it has any at all has to do with the rows of zeros. In this case, there's a single row of zeros, which corresponds to this C. And if C is not equal to 0, there are no solutions, because the first equation says 0 times something is equal to C. And if C is equal to 0, then the number of solutions is this number of free variables. There are infinitely many, and they correspond to these free variables. Let me do a slightly different kind of example. Suppose I had a tall skinny matrix like this, which looked like 1, 0, 0, 1, 0, 0, 0, 0. Now there are only two variables, x1, x2, and this is equal to b1 down to b4. Okay, how many solutions does this equation have? Well, there are no free variables. Right, because you look here, every row has a pivot, or another way to say it is that the rank of this matrix, the number of non-zero rows, is 2, and the number of columns is 2, so there are no free variables. And how many solutions does this have? Well, this is simply the set of equations. x1 is equal to b1, x2 is equal to b2, and 0 is equal to b3, and 0 is equal to b4. So the answer is there's one solution, if B3 and B4 are both 0, and no solutions otherwise. So you see that the sort of main bifurcation is between no solutions and some solutions. And if there are any solutions, in this case, there's a unique solution because the number of free variables. The reason you have exactly one solution here is that because the number of free variables is 0. There aren't any free variables. Okay, I think that's all I will cover for now. Next time I will discuss the actual procedure of row reduction to a row echelon form and do a couple of examples and talk about the homogeneous case.